All right, everybody. It is time for some new lessons and some new topics. um, well, that's not entirely true. Yes, we're going to learn about some new things, but it comes directly from where we cut off from the last test. Okay, so I thought, just for my own peace of mind, and because I thought it would help, at least some students, I thought it'd be good to start off with the last thing that we were doing uh, before this video came to be. Okay, and then that will be the perfect segue into what we need to cover next. That's new, right? So let's talk. All right. So the new topic is something called the binomial distribution, but that's based on something called a random variable, which is something we talked about before, but specifically a discrete random variable. So here's what a discrete random variable is. Let's start by all thinking about that. Okay. So for a discrete random variable, there has to be a probability experiment, which, experiment makes it sound scientific, like it occurs in a laboratory. But a probability experiment could be flipping a coin, rolling a dice, choosing a card from a deck of cards. It could be an experiment in a laboratory, but it's like a probability experiment is something with an unpredictable or random outcome. All right. That's what makes it a probability experiment. The fact that you don't know what's going to happen. All right. Now, for a discrete random variable, the probability experiment that it's based on, there has to be a limited number of possible outcomes. All right. So there can't be like some unconceivably great number of possible things that can happen. There might be like 5 things that could happen. Well, like say you roll a dice. There are 6 things that can happen. You could roll 1, 2, 3, 4, 5, or 6. Or I guess the dice could fall off the table and you'd lose it, where there are 7 things that could happen. Maybe, well, anyway, so you get the idea. So there are a limited number of possible outcomes. And the random variable part of it, which we'll call, we'll give it a letter, we'll say X, normally is the thing we use for a variable, will be a value associated with each outcome of the experiment. Now, I think it's hard for some people to learn things just through definitions. We have to have definitions though, but a definition plus an example to go along with it will help you see what you need to see about it and understand what you need to understand. So here's an example of a random variable. Okay, so remember, it all starts with a probability experiment. So let's say we toss 2 coins and we observe the number of heads. Okay, and well, that's definitely a probability experiment, and there's a limited number of possible outcomes, right? Okay. Well, how many outcomes? There's only like 3 things that could happen, really, as far as the random variables goes. All right. And so the random variable will be the number of heads you observe between the 2 coins. Okay. Well, okay. So what are the possible values for the random variable? You toss 2 coins. You count how many heads there are between the 2 coins. Well, there could be none, there could be 1, or there could be 2. There's 2 coins, okay? So the possible values for the random variable are 0, 1, or 2. Now, that's the setup, and like, for me to take it up to right here, that's what a random variable is. Now, where we go further than that in statistics class is we calculate probabilities, we calculate the odds that something will happen. It's not just enough to say, well, here's what might happen, but we want to say how likely it is, how probable it is, and so on. So here's where I want to take it from here. What are the probabilities that the random variable will be 0 or 1 or 2? Those are the only possible values it could take. So the way I did this particular problem to tell you those probabilities is I wrote down the sample space. What's a sample space? For a probability experiment, the sample space is a listing of every possible outcome. All right, so what was the experiment? Toss 2 coins. Here's the sample space for that experiment. Tails, tails, tails on both. tails on the first one, heads on the second, heads on the first one, tails on the second, and then heads on both. That's everything that could happen. Like, there are no other possibilities, are there? Now with that, if that's the whole sample space, I can tell you the probability that the random variable will take any of its values. What's the probability that the random variable is 0, that there's no heads among the two coins? Well, that can only happen one way. See this? Heads, heads. Out of 4 total outcomes, you got a 1 in 4 chance, 0.25 chance, 25% chance. What's the probability that the random variable will be 1? Meaning that you toss 2 coins and you see that there's 1 head between the 2 coins. Well, that can happen in 2 ways. You see, you can get tails on the first, heads on the second, or heads on the first, tails on the second. So that's 2 ways out of 4, which is 1 out of 2, or 0.5, or 50%. And then the probability that there are 2 heads among the 2 coins, that can only happen in one way, and there are 4 total outcomes, so it's a 1 out of 4 chance, or 0.25. Okay, so I've got my probability experiment. I defined my random variable. Then I calculated the probabilities that it would take any of its values. Now, we get 2 things from that. We get the probability distribution for the random variables. That's this. The random variable is x, the number of heads you observe between 2 coins that are tossed. It could be 0, 1, or 2. And the probability that it takes any of those values as we calculated. So this table is the probability distribution for the random variable. Now, you could also, almost anything you can do in math with a table or a listing of numbers or whatever, you can do with a graph. So this is the graph of it, of the probability distribution. And it's the same information. The graph is just a picture, all right? So it's like, okay, x is the random variable. It's the number of heads. You see that 2 right there? Okay, so if you go vertically, that's the probability that it's 2. It says 0.25. That's what it is, all right? So now that's the story with discrete random variables, all right? You get a probability experiment. The random variable refers to the outcome somehow of the experiment. You know, it's going to be a number, and then you could calculate the probability that it is any of those numbers that it can take. And you get the distribution and the graph. Okay, now, here's where the new topic starts. We need to learn what a binomial experiment is. And it will probably seem like a lot of information to take in at first, but we'll go through it in description and then some examples. Okay, so with a binomial experiment, it starts with a probability experiment. Okay, so some situation where you do something and you don't know what's going to happen. Okay, there has to be a fixed and definite number of trials. It can't be open-ended, in other words. Okay, so I have to say, like, well, we're going to do something 20 times and we're going to watch what happens each time, right? It's got to be definite, can't be open-ended. Okay, and each trial of the experiment is independent of all the other trials. Well, what does it mean when I say they're independent? That's a word we've used before when we learned about probability and just calculating probabilities. For me to say that the trials or each trial of the experiment is independent of the others means that whatever happens in one trial can in no way influence what happens in the next one or any of the others. Okay? One thing that's like that is flipping a coin. We talked about that. Say you flip a coin, you get heads. And say you pick it up and you're going to flip it again. Does the fact that you just got heads, could that have anything to do with what happens when you flip it again? Like, the coin forgets it. It doesn't know. Okay? So what happens with one coin flip has nothing to do with what's going to happen in the next one. All right? That's an example of doing something repeatedly where each time you do it's independent of every other time. Okay? All right. Now, no matter what the nature of the experiment is, now remember, in a probability experiment, we don't know what's going to happen. The outcome is random. But in a binomial experiment, well, think of the prefix bi, meaning two. No matter what the nature of this probability experiment is, there's only two mutually exclusive outcomes. All right, and we'll call one of them success and one of them failure. And I guess which one is success and which one is failure could be a matter of opinion, but there's just two mutually exclusive outcomes. All right, just two, no more than that. Now, what do I mean by two? Well, not just two, exactly two, no more than two, no less than two, two. But what do I mean when I say mutually exclusive? Well, that's another term we introduced when we first learned how to calculate probabilities. And mutually exclusive events or mutually exclusive outcomes cannot both happen, okay? Like when you flip a coin and you say, well, I could get heads or I could get tails, but I can't get both. Those are mutually exclusive outcomes, mutually exclusive events. They cannot both happen, okay? So in a binomial experiment, there's just two things that can happen and they're mutually exclusive, meaning they both can't happen at the same time. And we'll call one success and one failure. Now, the probability of success then on every trial does not change. It doesn't get more likely as you go on or less likely as you go on. Like when again, flipping a coin is an example of this. When you flip a coin, you could say the probability of heads is a half. But that doesn't change as you keep flipping it. It's still a half every time. Like, what would change it? What would make it different? All right. So in a binomial experiment, same thing. The probability of success, whatever you consider success to be, is the same for each trial. It does not change. Okay. Now, the random variable aspect of this is x, and we'll say it counts the total number of successful trials out of how many there are. Remember I said there's got to be a fixed, definite number of trials. It can't be open-ended, all right? Now, when we do math, there's symbols and all that kind of stuff. So here are the symbols that go along with it. N is the total number of trials. Remember, there's got to be a fixed, definite number of trials. P will be the probability of success, and Q will be the probability of failure. Because remember, there's just two mutually exclusive outcomes on any one trial, success or failure. Like you flip a coin and say, if it's heads, it's a success, and maybe I win. If it's tails, it's a failure. Okay, but P will be the probability of success, and Q will be the probability of failure. Now, because there's only two outcomes in a binomial experiment, then and they're mutually exclusive, those probabilities of success and failure have to add to 1. So if P is the probability of success, Q, the probability of failure, will be 1 take away P. All right. So that's like, still, again with the coin flip. If probability of heads is a half, what's the probability of tails got to be? All the probabilities of everything that can happen, every individual outcome has to add to 1. So 1/2 plus what is equal to 1? 1/2 plus 1/2 is equal to 1. So probability of heads and tails are each a half. And X is the random variable that counts the number of successes out of the indefinite number of trials. So X could be no successes, 1 success, 2 successes, and so on. Okay, now, so that's what it all is. I try to explain it, but that's just me explaining it. We need an example, right? Okay. So let's say that we'll have this like kind of quiz aspect to the video. Or say, is this a binomial experiment or not? Where the definition and specifications are given up here. All right. Okay. Suppose you flip a coin 5 times. Flip it once, pick it back up, flip it again, pick it back up, flip it 5 times, and observe if heads or tails on each flip. Okay. The random variable X will be the total number of heads out of 5 trials. Oh, okay. All right. So does this satisfy everything that is true for a binomial experiment. Well, are there a definite number of trials, or is this open-ended? Oh, there's a definite number of trials. There's 5, right? So yeah, I mean, so let me say like check, okay? What was the next thing? Is each trial independent of the other trial? Like, so if I'm gonna flip this coin 5 times, and I'm gonna notice if I get heads or tails each time. Is the first flip, does that have anything to do with the second or the third? And does the second have anything to do with the third or the fourth? Or do any of them have anything to do with any of the others? No, I mean, coin flips by nature don't influence each other. So yes, all the trials are independent. All right. What was the other thing? Oh, there has to be only 2 outcomes on any trial. Well, if you flip a coin, if we're going to ignore the fact that you could lose the coin if it falls off the table, then yes, there are only 2 outcomes. And we could consider like, well, this would be a matter of opinion, how you're framing the experiment, but there's only 2 outcomes for sure. That's not a matter of opinion. And we could say, well, if you get a heads, that could be success, and if you get a tails, that could be failure. Okay. And maybe the random variable counting the total number of heads out of the 5 trials implies that. All right. Now, what was the next thing that has to happen? Does the probability of success, however you're defining it, is it the same for each trial? Well, yeah, you flip a coin over and over. You know, it's going to be 1/2 is the probability of heads every time. So yeah, it's not changing. Okay. And so yes, it satisfies all those things. The random variable x could take the value 0, 1, 2, 3, or 5. 3, 4, or 5. Okay. What if x was 0? What would that mean? It would mean out of 5 flips of a coin, I didn't get any heads at all. That's what the significance of the random variable being 0 is. What if the random variable were 3? The significance of that would be I flipped the coin 5 times and 3 heads were observed. Okay, so this is a binomial experiment for all that, like through my checklist. I just verified every aspect of that original definition. Okay, so now let's try another one, still in quiz format, right? Binomial experiment or not. Suppose a machine contains balls in it, and with this I'm thinking like you've seen, I don't know how they do the lottery anymore, but it used to be there's this thing that rotated all these balls around. They had numbers on them, and then it would spit one out. I mean, that would be one of the winning numbers, okay? So suppose a machine contains balls with numbers 1 through 30 and randomly dispenses a ball, which is not replaced. Okay, so the ball comes out, maybe the number on it is noted or recorded, but then it's not put back in there for the next one to be spit out, all right? Okay, so before each ball is dispensed, you try to guess what it will be, all right? So maybe this is like a kind of gambling game, like the lottery. And of course, if you try to guess what it's going to be, you're either right or you're not, all right? You'll get 5 total attempts at this. The random variable x will count the number of total correct guesses out of the 5 trials, okay? Now, this one turns out not to be binomial. I'll go through all the reasons and I'll talk about it, and I'll tell you why, what about it makes it not binomial. Now, there are a definite number of trials, okay? There's 5, right? You're playing this guessing game, and you're either right or not each time. Okay. 5 times, you get 5 attempts. You guess, it spits out the ball, you're either right or wrong. You make another guess, it spits out the next one, you're either right or wrong. Okay, so there's a definite number of trials, 5. And there's only 2 outcomes on each trial. Yeah, because like you're guessing and you're either correct or you're not. So we could say success was correct and failure was incorrect. Okay, so it does that aspect of it too. Here's where it fails to be binomial. The trials, the individual guesses, are not independent of each other. And as a result, the probability of success will vary by trial. So let me show you how this is. Say you're playing this game. First ball's about to come out, and you place your guess. There are 30 balls in there, and so you got a 1 in 30 chance of being right. Okay? All right. And then you note success or failure based on that. Then that ball is not replaced. And before the second ball comes out, you make your next guess. And there's only 29 in there now, and you got a 1 in 29 chance of getting that second guess correct. So because you're not replacing the balls, the trials aren't independent, and the probability of success is not fixed. Remember, we said up here that there is going to be just success and just failure, but the probability of success has to be the same every time. And here, at least with this game, with this experiment, the probability of success actually becomes a little more likely. 1 out of 29 is a little more likely than 1 out of 30. What would the third ball be? What's the probability of success on the next one? 1 out of 28, because every time one of the balls is dispensed, you're not replacing it. Okay. All right, let's try another one. So let's say now this experiment is based on a previously done survey. So there's two aspects to this example. There's a survey to gather some information, and then there's a probability experiment. So suppose there's a survey of 1,000 employed people, and they were asked the question, has the economy forced you to reduce your spending on non-essential items this year? Things you don't have to buy. And the results were that 72% answered yes to that question. Okay. And I guess the other 28% did not answer yes. Maybe they said, leave me alone. Maybe they said no. Maybe they just walked away. Like, imagine if somebody's surveying. So there's yes, and then there's everything else. Okay. So the problem now, say that's the information. Okay. Here's a probability experiment based on the survey. Suppose out of that group of people surveyed, we randomly select 30 of the people, and the random variable x will count the total number of workers or employed people who answered yes to that question, okay, out of the 30. So you've got this pool of 1,000 people, and you take 30 of them, and you see, well, how many of you 30 answered yes to that survey question? The random variable counts how many of the 30, okay? All right, so as this probability experiment is defined, like you're going to take the 30 people, and you're going to look at the first one. You say yes or no, okay? Then you go to the next one, yes or no. Then you go to the next one, yes or no. You see what I mean? For all 30. That's the probability experiment. Is that binomial? It turns out that is binomial. There's a definite number of trials. There's 30. You go through all 30 people randomly chosen. Say, did you answer yes to the survey question or not? Okay. The trials are independent. I mean, you randomly choose this group of 30 people, and then you like look at the first one. Did you answer yes or no? Did you answer yes or no? Did you? And like, but how you record the answer for the first one has nothing to do with the answer for the second one. They've already answered. Their answers are established. You're just making a random selection. So the trials are independent. As you go through that group of 30 people, their answers have already been recorded, and they're not going to change, okay? So the recording yes or no, did you answer yes or no to that question? As you go one by one, they're definitely independent of each other. Like what happens on one can't affect the others at all. Okay, and there's only two outcomes on any trial. The trials being going through the 30 people and saying, did you answer yes or not? If you answered yes, maybe you'd call that success. And if they did not, if they walked away or said, leave me alone, or said no, that would be failure. Okay, but there's just two outcomes. They either answered yes or they didn't. Okay, all right, well, now we can give some of the numbers that go along with a binomial experiment. Okay, this is a binomial experiment. It satisfies every aspect of a binomial experiment as originally given here. But let's give some of these. There are symbols in math, as I said, so on and so forth. Let's give some of the symbols for this one. N is the number of trials. P is the probability of success on any trial. Q, the probability of failure. And X, the random variable that counts the number of successes out of the n trials. So here's what we would do. I would say, okay, yeah, this is a binomial experiment. There are 30 people randomly selected. Because the original survey said that 72% of the 1,000 answered yes to the question, then any one of those people, I'd say, has a 72% chance of having said yes. Okay, so like P, the probability of success, the probability that any one of the 30 people that you're looking at answered yes to the question, is 0.72. And Q, the probability of failure, or that they did not answer yes, is 1 minus 0.72, which is 0.28. And then X is 0, 1, 2, 3, all the way up to 30, okay? All right, so that's all how the notations will work out. So I wanted to do two things with this one. I wanted to confront you with the situation and see if you could understand all my reasons for saying that it was a binomial experiment, okay? Now, one thing that I'm worried gets lost in all this is the nature of the experiment and the trials, okay? So the experiment is to select a group of 30 people, and the trials is to go through them one by one and say record if they answered yes to the survey or not. So for the random variable, like just for the sake of example, if X was 5, then here's what that would mean. It would mean 5 of the 30 people selected answered yes to that survey question. Okay? Okay, anyway, so now we've seen a little bit of everything. Where do we go from here? Well, think about it. Like, I have given you the probability as you go through this group of 30 people that any one of them answered yes to the survey question, 72% chance that they did. But like, how would you like say calculate the odds or the probability that 5 of the 30 people randomly selected answered yes to the survey question, or 30 out of the 30 people, or 20 out of whatever? Okay, so there are lots of ways that we can do that. There are formulas that you can write down and use a calculator and paper. Excel is, I've used Excel a little bit in some of the videos. My math lab has StatCrunch in it. It's included. You already have my math lab if you're doing the homework, and it's got StatCrunch built into it. And you could use that. That's real easy. So in the next video, we'll talk about how you do some of the calculations.